Right now, 16,000 scientists are listening for a signal that will change everything. Every major radio telescope on Earth points toward the cosmos, waiting. The search has been running for 64 years without a single confirmed contact. But the Drake equation tells us something disturbing. With 400 billion stars in our galaxy alone, the odds say intelligent life should be everywhere. Fermi asked the question that haunts every astronomer. Where is everybody? In 2017, Oumuamua passed through our solar system, moving in ways no asteroid should. Its acceleration defied natural explanation. Scientists proposed 17 different theories, but none fit perfectly. Then, in 2021, the Pentagon confirmed 143 encounters with objects that break the laws of physics as we understand them. We are either alone in a universe that should be teeming with life, or we are being watched by something that chooses to stay hidden. Both possibilities terrify us equally. The question is no longer if we will make contact. The question is what happens the moment we do. If you find this unsettling, hit that like button and subscribe. We begin now. We didn't decide to announce ourselves to the cosmos. The decision was made for us. In 1920, station KDKA in Pittsburgh sent out the first commercial radio broadcast. That signal traveled through the atmosphere and kept going, out past the moon, out past the planets, into interstellar space at the speed of light. 100 years later, it's still traveling, still moving outward in an expanding sphere, still carrying the voice of someone who never imagined their words would leave the solar system. Every radio transmission we've ever made has done the same thing. Every television broadcast, every radar ping bouncing off an airplane, every microwave tower relaying a phone call. They don't stop at the edge of our atmosphere. They leak into space and keep traveling forever. Our earliest broadcasts from the 1920s have been traveling for roughly 100 years. That sphere of human noise is now 200 light years across. Inside that bubble are about 15,000 stars, 15,000 solar systems that could, in theory, detect us, that we've been shouting at for a century without asking if anyone was listening. Right now, at this very moment, the finale of Meishi is washing over a star system 40 light years away. Goodbye, farewell, and amen is traveling at the speed of light towards something that might be listening. The most watched television episode in American history, carrying the voices of actors who are gone, reaching worlds that might not have eyes to see or ears to hear. We've already made first contact. We just don't know if anyone picked up the phone. Think about what that means. The first episode of I Love Lucy aired in 1951. That signal is currently 70 light years away, passing stars we can barely see with our best telescopes. Lucille Ball's laughter is arriving at solar systems that might have no idea what laughter is. Every gesture, every pratfall, every joke about Vitamiata Vegamin encoded in electromagnetic waves and delivered to the void. If something out there has the right equipment and happens to be listening, they're watching the 1950s unfold in real time. History arriving as breaking news. The moon landing is even more recent. 1969 was only 54 years ago in cosmic terms. If aliens 50 light years away tuned in right now, they'd be watching Neil Armstrong step onto the lunar surface for the first time. One small step for man. They'd be hearing it as we heard it, delayed and crackling, a voice from another world announcing that we'd finally left our own. They'd have no context for what they were seeing, no way to know if this was routine or revolutionary, just images of creatures in white suits moving across a grey landscape under a black sky. Our radio bubble spans 200 light years in a galaxy that's 100,000 light years across. Picture lighting a candle in a football stadium and hoping someone on the other side notices. The light exists. It's real, but the stadium is so vast that even the brightest flame becomes invisible after a certain distance. Our transmissions weaken as they spread. The inverse square law dilutes them. By the time our signals reach the nearest star system, they're barely distinguishable from background radiation. Picking them out would require equipment we can barely imagine. It would mean someone was listening very carefully, and that they wanted to hear us. When we talk about finding aliens, we usually imagine building a big telescope and searching the sky. Actually, that's not quite right. The real question isn't whether we'll find them, it's whether they've already found us. Whether something out there in one of those 15,000 star systems has been watching our bubble expand for decades. Whether they tuned in during World War II and tried to make sense of what they were hearing. Whether they've been tracking our technological development through our electromagnetic signature, waiting to see if we survive our own adolescence as a species. We assume first contact will be a deliberate act, a message crafted carefully, vetted by committees, approved by governments, something momentous and intentional. But we've been broadcasting continuously for nearly a century. Every Cold War transmission, every satellite uplink, every television show, every radio drama, every emergency broadcast, every transmission from every antenna we've ever built has leaked into space and kept going. The decision about whether to contact aliens was made in the 1920s by people who had no idea they were making it. The bubble is still growing. Right now, today, signals from the 90s are washing over stars 90 light years away. Someone out there might be discovering Friends for the first time, or watching the fall of the Berlin Wall, or hearing about the Challenger disaster as breaking news 38 years after it happened. Time doesn't compress, it just travels. Every moment we've broadcast is still out there somewhere, moving away from us at light speed, creating a chronological record of humanity that anyone with the right receiver could access. There's something unsettling about that. We can't take it back. We can't edit it. Every broadcast, every transmission, every signal is a permanent record, traveling outward forever. If there's intelligent life within our bubble, they know more about us than we know about them. They've had decades to study us, to listen to our music, to watch our wars, to hear our hopes and fears encoded in sitcoms and news broadcasts and emergency alerts. We're visible. We've been visible for 100 years, and we have no idea if anyone's watching. This changes the question entirely. We don't ask anymore if we should send a message to the stars. We've already sent millions of them. The question now is whether we're listening carefully enough to hear what comes back, whether something in those 15,000 star systems is preparing a response, or whether they've decided that what they've heard is reason enough to stay silent. The universe has been receiving our transmissions for a century. What we need to understand now is what it means to search for a reply. We've been broadcasting for 100 years. The question now is what we're actually trying to find. Looking for aliens is like being a detective, where the suspect could be anything from a bacterium to a Dyson sphere. You're searching for evidence of a crime before you know what crime you're investigating. The suspect might be microscopic. It might be larger than a star. It might have been dead for 1 billion years, or it might be watching you right now. That uncertainty shapes everything about the search. We've divided the possibilities into 3 tiers, 3 categories of discovery that range from the simple to the profound: microbial life, complex life, and technological civilizations. Each tier answers different questions. Each one changes humanity in different ways. Start with the first tier: microbial life, single-celled organisms, bacteria, archaea, things so small you'd need a microscope to confirm they exist at all. This is the baseline, the simplest form of biology we can imagine, just chemistry that copies itself. Finding bacteria on Mars would be like discovering a second Genesis, proof that life's origin wasn't a one-time miracle, but a repeatable chemical process. That's what makes it revolutionary, not the discovery itself, but what it implies. If life started twice in one solar system, then the universe isn't just capable of producing life. It's probably full of it. The numbers shift entirely. If Earth and Mars both have life independently, then the odds of life emerging anywhere with the right conditions go from a cosmic lottery to a near certainty. Every planet with liquid water becomes interesting. Every moon with a subsurface ocean becomes a candidate. We go from possibly alone to probably surrounded. That's tier 1. the most likely discovery, the one that changes everything while remaining invisible to the naked eye. Tier 2 is complex life, multicellular organisms, things with specialized cells, organs, nervous systems, plants, animals, anything that required billions of years of evolution beyond that first cell. This is dramatically less likely than microbes, but it's what most people picture when they hear the word alien, something that moves, something that responds to its environment in ways we'd recognize as behavior. We have no idea how common this is. Life on Earth spent 3 billion years as nothing but single cells. 3 billion years. That's 3/4 of Earth's entire history. Complex life is a recent development, and we don't know if it was inevitable or a statistical fluke. Maybe every world with microbes eventually produces complexity. Maybe Earth is the only place in the galaxy where cells learned to cooperate. Finding complex life would tell us that evolution has a direction, that given enough time, biology doesn't just survive, it elaborates, it experiments, it builds structures sophisticated enough to be visible from orbit. The third tier is technological civilizations, intelligence, beings capable of altering their environment in detectable ways. This is the rarest possibility and the most profound. It's also the only tier that might find us first. Technology leaves marks, signatures we can detect across light years, radio transmissions, artificial light on the night side of a planet, atmospheric pollution, industrial chemicals that biology would never produce, megastructures that block starlight in patterns too regular to be natural. We call these technosignatures, and they're what SETI has been searching for since 1960. Finding a technosignature wouldn't just mean we're not alone. It would mean someone else figured out what we figured out. That intelligence isn't unique to Earth. That consciousness, language, tool use, science, all of it can emerge independently. That the universe doesn't just make life, it makes minds. Here's the part that gets me. All three tiers are equally important. We treat the search for technological civilizations as the grand prize, but that's not quite right. Finding bacteria on Mars would be as revolutionary as finding a radio signal from Proxima Centauri. Both discoveries answer the same fundamental question. Are we alone? Both give the same answer. No. The difference is what comes after that no. Bacteria tell us life is common. A radio signal tells us we might have peers, someone to talk to, someone who's been asking the same questions. The search itself comes down to signatures, chemical fingerprints, biological indicators, signs of technology. We're not looking for the aliens themselves. We're looking for what they leave behind. Biosignatures are chemical indicators of life. Oxygen in an atmosphere, methane, phosphine, gases that biology produces and that wouldn't persist without something continuously making them. Earth's atmosphere is 21% oxygen because plants and algae produce it faster than chemistry can remove it. Without life, that oxygen would vanish in a few million years. Oxygen is evidence. It's a signature. The James Webb Space Telescope can detect atmospheric composition of exoplanets. It analyzes starlight filtering through alien atmospheres during transits. Different molecules absorb different wavelengths. We can read the chemistry of a world we'll never visit, looking for combinations that don't make sense without biology. Technosignatures are evidence of technology, radio signals, laser pulses, heat signatures from artificial structures, atmospheric pollution from industrial processes. These are harder to find because they require a civilization to be active right now, in the tiny window where we're listening. But they're also unmistakable. Nature doesn't produce narrowband radio signals. Nature doesn't build things that glow at infrared wavelengths characteristic of waste heat. Searching for technosignatures is like walking through a forest trying to find signs of human presence. You're not looking for the humans themselves. You're looking for the campfire smoke, the carved tree trunks, the footpaths worn by repeated passage. The marks we make on the environment persist longer than we do. Finding life doesn't mean finding intelligence, but finding intelligence definitely means finding life. The tiers are nested. Technology requires complexity. Complexity requires microbial origins. You can't skip steps. That's the structure of the search. 3 possibilities, 3 tiers of discovery. Any one of them rewrites the textbooks. Any one of them forces us to reconsider our place in the universe. But there's a problem. We're not even sure we'd recognize alien life if we saw it. Our entire definition of life is based on a sample size of 1. Earth. We look for water because water is what we needed. We look for carbon because we're made of carbon. We search for DNA, for cells, for metabolism that resembles ours. But there's no law of physics that says life must be like us. Life might not need water. It might use ammonia or methane or something we haven't considered. Life might not be carbon-based. Silicon can form complex molecules. So can other elements under the right conditions. Life might not even be chemistry as we understand it. It could be patterns in plasma, self-organizing structures in exotic matter, processes so alien we wouldn't classify them as alive. We might have already found alien life and dismissed it because it didn't fit our checklist. Viking landers on Mars in the 1970s detected chemical reactions in the soil that some scientists still argue could be biological. We ruled them out because they didn't match our expectations. We're looking for our reflection, and that might be exactly the wrong strategy. The universe doesn't care what we find convenient. It doesn't care that we're only equipped to recognize one kind of life. If biology emerged differently somewhere else, using different chemistry, following different rules, we might look right at it and see nothing but noise. That's the uncertainty at the heart of the search. We've built our detection methods around what we know, but what we know is limited, narrow, based on one example. Still, we search, because even a narrow search is better than no search at all, because finding anything, even something familiar, would prove that Earth isn't the only experiment, because the alternative is assuming we're alone, based on our failure to look carefully enough. Any detection, even the simplest, changes everything. A microbe on Mars, a chemical signature in an exoplanet's atmosphere, a radio signal from a distant star. Any of these would be the most important discovery in human history. The question isn't whether we'll find something. The question is what that something will be, and whether we'll know it when we see it. Before we can recognize alien life, we need to know what life is. Not the poetic version, not the philosophical one, the chemical version, the bare minimum requirements that separate life from not life. Strip it down to fundamentals. Life needs an energy source, something to power the processes that keep it running. For us, that's sunlight or chemical reactions. Life needs a liquid medium, some kind of solvent where molecules can meet, interact, build complexity. For us, that's water. Life needs chemical building blocks, elements that can combine in complex ways. For us, that's carbon and amino acids. Life needs containment, a boundary that separates inside from outside. For us, that's cell membranes. Life needs heredity, a way to store information and pass it on. For us, that's DNA. Those 5 things: energy, liquid, chemistry, containment, information. That's the recipe we're working from, the only recipe we have. Because Earth is our only example, we assume these requirements are universal. Maybe they are. Maybe life everywhere follows these same rules, just with different ingredients. Or maybe we're completely wrong. Think of it this way. Life is less like a machine with specific parts and more like a fire. It doesn't matter what's burning as long as there's fuel, heat, and oxygen. The specifics might change, but the principles remain. A campfire burning wood and a candle burning wax are both fire. They operate on the same fundamental process. Even though the materials are different, life might work the same way. Different materials, same underlying principles. Earth's life is carbon-based. Carbon is special because it forms long, complex chains. It bonds with almost everything. It creates the scaffolding for proteins, DNA, all the machinery of biology. Silicon is the only other element that comes close. It sits right below carbon on the periodic table, shares similar bonding properties, but silicon chains are less flexible, less stable in water. Carbon wins, at least here. Water is special too. It stays liquid across a wide temperature range, from 0 to 100 degrees Celsius. That's a comfortable window for chemistry to happen. Water is an excellent solvent. It dissolves more substances than almost any other liquid, which means it facilitates reactions. Earth is the only place in our solar system where water exists in all three phases naturally: ice, liquid, vapor, all present at the same time. We assume aliens would need something like water, but maybe they use liquid methane, maybe ammonia, maybe something we haven't imagined. The principle is the same: a liquid medium where chemistry can occur, but the specific liquid might be different. Here's where it gets interesting. In 1969, a meteorite fell near Murchison, Australia. When scientists analyzed it, they found amino acids, the building blocks of proteins, more than 90 different types. These weren't contamination from Earth. They were formed in space, delivered by a rock that had been drifting for billions of years. Amino acids arriving on meteorites are like care packages from space, delivery confirmation that the universe is running chemistry experiments everywhere. Not just here. The raw materials for life aren't unique to Earth. They're out there, forming in molecular clouds, hitching rides on asteroids, raining down on every rocky planet and moon. The ingredients are common. The universe is soaked in organic chemistry. That should excite us. If the building blocks are everywhere, maybe life is everywhere too. Maybe the hard part isn't getting the ingredients. Maybe the hard part is something else. Here's what we don't talk about enough. We've never created life from scratch, not once. We can modify existing life. We can splice genes, clone animals, edit DNA with precision. We've built bacteria with artificial genomes, but we cannot take raw chemicals, mix them in a lab, and make them alive. We've tried. We've recreated early Earth conditions. We've simulated hydrothermal vents. We've zapped chemical soups with lightning. Nothing. No spark. No transition from chemistry to biology. We don't actually know how life starts. We have theories. The primordial soup hypothesis. Organic molecules in a warm pond, energized by lightning or ultraviolet light. The hydrothermal vent hypothesis. Life beginning in mineral-rich water, spewing from cracks in the ocean floor. Panspermia. The idea that life didn't start on Earth at all, but arrived from space, already formed. All of these are plausible. None are proven. The origin of life remains one of the deepest unsolved problems in science. We're looking for alien life without fully understanding our own. We're searching for something we can't even create in controlled conditions. Think about that. We're about to spend billions scanning the cosmos for biology, and we don't know what makes chemistry become life. Maybe that's okay. Maybe you don't need to understand how fire starts to recognize it when you see it. You know it by its properties. It consumes fuel. It releases energy. It spreads. Life is similar. You know it by what it does, not by how it began. Asking, what is life is like asking what is a wave. You can describe its properties, its behavior, its requirements, but the answer changes depending on whether you're talking about ocean waves, sound waves, or quantum waves. They're all waves. They all follow wave mechanics, but they're made of completely different things. Life might be the same. A pattern, not a thing. A process that can emerge from different substrates. This is the first emotional peak, the realization that should shake us. Life might be simpler than we thought. Not easy, but not impossibly rare. The ingredients are common. The chemistry happens everywhere. Meteorites are delivering organic molecules to every corner of the solar system. If life is a natural outcome of chemistry under the right conditions, then the universe should be teeming with it. Or we're completely wrong about what life requires. Maybe carbon and water and amino acids are optional. Maybe life can be made of things we haven't considered. Plasma beings in the atmosphere of a gas giant. Silicon networks in the crust of a frozen moon. Information patterns in quantum fields. We'd never recognize those as life because they don't fit our template. We're trapped by our own biology. Every definition of life we create is based on Earth. Every search parameter is calibrated to find ourselves. That's not arrogance. That's limitation. We only have one example, one data point. You can't draw a line with one point. You can't establish a pattern. You can only guess. The humbling truth is this. We're searching for something we can't define perfectly. We know life when we see it on Earth, but we might miss it everywhere else. We're looking for a pattern we've only seen once, hoping it repeats, terrified it might not. The requirements might be universal, or they might be local, specific to this planet, this star, this moment in cosmic history. That's the uncertainty we carry into the search. That's the weight of our ignorance. We need energy, liquid, chemistry, containment, heredity, but maybe aliens need something else entirely. Maybe they'd look at Earth and wonder how life could possibly survive in such bizarre conditions. Maybe our kind of biology is the weird one. What we do know is this: life on Earth exists in places we once thought impossible. Scalding hot, frozen solid, acidic, radioactive, crushing pressure, no sunlight. If life can thrive there, what does that say about everywhere else? Let's see if those places really are impossible. Yellowstone National Park, geysers erupting, pools of water superheated to 212 degrees Fahrenheit. That's boiling temperature. The heat that cooks pasta and kills bacteria on your dishes. Nothing should live there, but something does. Thermophiles, microorganisms that don't just survive boiling water. They thrive in it. They require it. The colorful rings around Yellowstone's hot springs aren't minerals. They're living communities. Bacteria in reds and oranges and yellows, feeding off the heat and chemicals that would denature your proteins in seconds. Some thermophiles live at temperatures exceeding 122 degrees Fahrenheit. Others push past that, into realms where water stays liquid only because of pressure. Take them out of their boiling pool and put them in your refrigerator, and they die. Not because they're fragile, because you've removed the conditions they evolved for. They're not tough, they're specialized. That's the pattern we keep finding. Earth's extreme is their normal. Go the other direction. Antarctica, Lake Vida, sealed beneath 65 feet of ice for more than 2,000 years. The water inside is negative 58 degrees Fahrenheit. That's well below the freezing point of normal water. It stays liquid because of salt concentrations 6 times higher than seawater. Nothing should survive that combination. Frozen darkness and brine so salty it would pickle your cells. But psychrophiles live there. Cold-loving microbes that adapted to a world without sunlight, without warmth, without any connection to the surface. They've been down there, isolated, evolving in their own direction while humans went from hunter-gatherers to space travelers. Then there are the halophiles, salt lovers. They thrive in concentrations that would kill most life. The Dead Sea, salt flats, brine pools at the bottom of the ocean. These organisms live in water so saturated with salt that it crystallizes on contact with air. Imagine trying to breathe air made of sandpaper. That's what normal water is to them. They've adapted so completely to high salt environments that fresh water would cause their cells to burst. Acid is supposed to dissolve life. Battery acid has a pH around 1. Stomach acid sits at 2. At those levels, most biological molecules fall apart. But acidophiles live at pH levels below 3. Some survive in pH 1. They've been found in acidic hot springs, in drainage from mines, in volcanic vents where sulfuric acid mixes with superheated water. Finding life in those conditions is like discovering someone who finds their living room too cold and prefers to nap inside a running microwave. It shouldn't work, but it does. Radiation is lethal. A dose of 500 rems will kill a human. 1,000 rems turns your DNA into confetti. The organism Deinococcus radiodurans survives radiation doses of 1.5 million rems. 1.5 million. That's 3,000 times the lethal dose for you. This bacterium was discovered in canned food that had been sterilized with radiation. The food was sterile. The can wasn't. Deinococcus radiodurans just sat there, unbothered. It's been found living inside nuclear reactors, feeding off the radiation we use to generate power. Its DNA gets shredded by gamma rays, and it just stitches itself back together, perfectly, every time. Pressure should crush life. At the bottom of the Mariana Trench, the deepest point in Earth's oceans, the pressure is over 1,000 times atmospheric pressure at sea level. That's 8 tons per square inch. Enough to collapse a human body like an empty can. But organisms live down there. Fish, amphipods, bacteria. They've adapted to pressure that would pulverize us. Their cells don't have air pockets that can collapse. Their proteins are structured differently. They're built for a world where the weight of the ocean is just background. Life has been found 2.5 miles deep in the ocean, in subglacial lakes sealed for millions of years, in clouds, in the upper atmosphere, in nuclear waste, in solid rock miles beneath the surface. That last one is worth sitting with. The deepest living organisms on Earth aren't in the ocean. They're miles beneath the surface, embedded in solid rock, living in slow motion. These endoliths have metabolism so slow that their cellular processes take centuries. A single generation, birth to reproduction, might outlast human empires. They don't eat organic matter. There isn't any down there. They metabolize minerals, iron, sulfur, hydrogen from the breakdown of water molecules in the rock itself. They live in pores and fractures, in spaces so small you'd need a microscope to see them. And they experience time differently than we do. Think about that. A life form whose heartbeat takes millennia, an organism that might reproduce once every 1,000 years. If life can do that here, what timescales might alien life operate on? We might be looking at living planets and seeing them as geologically active rocks because their heartbeat takes longer than recorded history. We could be staring at life and not recognizing it because it moves too slowly for us to perceive. Then there are the tardigrades, water bears, 8-legged microorganisms about 0.5 millimeter long. You need a microscope to see them, but they're everywhere. Moss, lichen, soil, ocean sediment. Tardigrades can survive being frozen, boiled, irradiated, and shot into space. They're basically the Nokia phone of the animal kingdom. They've been exposed to the vacuum of space and come back fine. Temperatures near absolute zero, -458 degrees Fahrenheit. They just enter a state called cryptobiosis, shut down all metabolic activity, and wait. Years, decades. When conditions improve, they rehydrate and go about their business like nothing happened. Radiation that would kill you 1,000 times over. Tardigrades shrug it off, pressure 6 times deeper than the Mariana Trench. They're fine. Boiling water, frozen solid, no water at all for years. They adapt, they survive. They've been on Earth for over 500 million years, outlasting most species that ever existed. They've survived every mass extinction event. They'll probably survive us. The point isn't that these organisms are tough. The point is that life is adaptable, wildly, unpredictably adaptable. We used to think life required sunlight. Then we found ecosystems around hydrothermal vents on the ocean floor, powered entirely by chemistry. We thought life required moderate temperatures. Then we found organisms living in boiling water and frozen brine. We thought life required neutral pH. Then we found it thriving in acid and alkaline extremes. We thought life required protection from radiation. Wrong again. Every time we've defined the limits of life, life has found a way past them. Earth's extremophiles aren't oddities. They're proof of concept, demonstrations that biology can adapt to conditions we'd consider uninhabitable. Each extremophile type maps onto a potential alien habitat. Thermophiles show that life could exist in hydrothermal systems on icy moons. Psychrophiles prove that frozen worlds aren't necessarily dead. Halophiles suggest that salty subsurface oceans might harbor ecosystems. Acidophiles indicate that acidic atmospheres or sulfuric clouds aren't automatically sterile. Endoliths reveal that life doesn't need a surface. It can exist deep underground, hidden from view, metabolizing the planet itself. And here's the thing, Earth's extremes are mild compared to what's out there. Yellowstone's hot springs are pleasant compared to the sulfuric acid clouds of Venus. Antarctica's ice is warm compared to the methane lakes of Titan. The Mariana Trench's pressure is gentle compared to the crushing depths of subsurface oceans on Europa. The radiation inside a nuclear reactor is nothing compared to the particle storms around Jupiter. If life can thrive in Earth's harshest environments, then the universe suddenly has a lot more real estate. A lot more places where biology might have taken root. A lot more worlds we need to examine closely. We're not looking for places like Earth anymore. We're looking for places with energy gradients, chemical potential, liquid of any kind, containers that can hold complexity. The requirements are broader than we thought. The possibilities are wider. Life doesn't need perfect conditions. It needs any conditions it can adapt to. And adaptation is what life does best. If life can do this on Earth, where else might it be hiding? The universe has real estate. That's what we just learned. Anywhere with an energy gradient, with chemistry, with liquid, anywhere life can get a foothold. And if that's true, we don't need to look light years away. We don't need interstellar probes or generation ships or warp drives. We might just need to look next door. Our solar system has ocean worlds, multiple ocean worlds, bodies with more liquid water than Earth, and we're only just beginning to understand them. Start with Europa, one of Jupiter's moons, slightly smaller than our own moon. From space, it looks like a cracked billiard ball, covered in fractures and ridges. That surface is ice, solid, frozen, ancient ice. Beneath it sits an ocean, a global ocean, 60 to 150 kilometers deep. That ocean contains twice the volume of water in all of Earth's oceans combined, twice as much. Under the ice shell of a moon orbiting Jupiter, Europa's ocean sits beneath an ice shell thicker than Mount Everest is tall, making it the most tantalizing and inaccessible body of water in the solar system. That ocean stays liquid because of tidal flexing. Jupiter's gravity squeezes Europa as it orbits. The moon stretches and compresses, like squeezing a rubber ball over and over. That squeezing generates heat, enormous amounts of heat, enough to keep a subsurface ocean from freezing for billions of years. And where there's liquid water, heat, and chemistry, there might be life. Not might be. The ingredients are there. Think about the pressure-loving microbes we talked about, the ones living in the Mariana Trench, thriving under crushing depths. Europa's ocean would be their paradise. The pressure down there makes Earth's deepest trenches look shallow, but pressure isn't hostile if you evolved for it. It's just home. The Europa Clipper mission launches in October of 2024. It won't land. It'll orbit Jupiter and make dozens of close flybys of Europa. It'll analyze the ice, sample any material ejected from the surface, look for signs of organic chemistry. We're sending a robot to taste Europa's ocean, not to drill through kilometers of ice, just to see what's being kicked up to the surface. Sometimes the evidence comes to you. Then there's Enceladus, a moon of Saturn, much smaller than Europa, only about 500 kilometers across. You could fit it inside Texas, but Enceladus doesn't hide its ocean. It advertises it. Enceladus is essentially advertising its ocean to us, spraying 250 kilograms of water per second into space like a planetary fountain, complete with organic molecules. We don't even need to drill. We just need to fly through the spray and collect samples. Those geysers erupt from the South Polar region, massive plumes of water vapor shooting into space. The Cassini spacecraft flew through them, analyzed what's in the spray: water, salt, silica, and organic molecules, carbon-based compounds, the building blocks of life as we know it, just floating there in the plume, free samples from a subsurface ocean. Enceladus is handing us the evidence. The ocean exists, that's confirmed. The geysers prove it. The question isn't whether there's liquid water. The question is whether anything lives in it, and we won't know until we go back with better instruments, with samplers designed to look for biology, not just chemistry. Here's the thing about extremophiles that gets me. They're not barely surviving, they're thriving. Boiling acid isn't hostile to them, it's home, which makes you wonder what looks hostile to us that's actually a paradise to something else. Titan is next, Saturn's largest moon, bigger than Mercury. It has lakes, actual lakes on the surface. You can see them in radar images, dark regions near the poles, shorelines, river channels feeding into them. Titan has a hydrological cycle: evaporation, clouds, rain, rivers, lakes, just like Earth. Except Titan's lakes aren't water. They're liquid methane at negative 290 degrees Fahrenheit. Swimming in them would be like diving into liquid nitrogen. But life doesn't care about our comfort zones. Titan has a thick atmosphere, mostly nitrogen, thicker than Earth's. The pressure at the surface is about 1.5 times Earth's sea level pressure. The sky is hazy, orange, dense, and the chemistry happening in that atmosphere is wild. Ultraviolet light from the sun breaks apart methane molecules. The fragments recombine into complex organic compounds, tholins, long-chain hydrocarbons. The air is full of organic chemistry, raining down onto the surface, accumulating in the lakes. Could life use liquid methane instead of water? Could it build cells with different chemistry, different solvents? We don't know. We've never seen it. But Titan is a laboratory, a place where we can test whether life needs water or just needs any liquid that can dissolve and transport molecules. The experiment is already running. We just need to go read the results. Mars is older news. We've been obsessed with Mars for over a century. Canals that never existed. Little green men that never were. But Mars has something real. Evidence of ancient water. Riverbeds carved into stone. Deltas where rivers once emptied into lakes. Minerals that only form in the presence of liquid water. Mars was wet. Billions of years ago it had rivers, lakes, maybe even an ocean in its northern hemisphere. That water is mostly gone now. Some escaped into space, some is locked in the polar ice caps, and some is still there, underground, as subsurface ice and possibly liquid brine. Mars has methane fluctuations, seasonal variations in atmospheric methane levels. Methane breaks down quickly in sunlight, so if it's in the atmosphere, something is producing it, either geological processes or biological ones. We don't know which. The question isn't whether Mars had the ingredients for life billions of years ago. It did. The question is whether life started, and if it did, is it still there, hiding underground, metabolizing in the dark, waiting for us to dig deep enough? Then there's Venus, hell world, surface temperature hot enough to melt lead, 470 degrees Celsius, atmospheric pressure 90 times Earth's, clouds made of sulfuric acid. Soviet probes that landed there in the 1970s lasted less than 2 hours before being crushed and melted. Venus is hostile, completely, utterly hostile. Except maybe it's not everywhere. At 30 miles up, Venus's atmosphere has Earth-like temperature and pressure. The temperature hovers around room temperature. The pressure is about the same as Earth's surface. You could stand there, in the clouds, without a pressure suit. You'd need an oxygen mask and protection from the acid, but the temperature and pressure wouldn't kill you. It's a habitable zone, in the sky, on Venus. In 2020, scientists announced the detection of phosphine in Venus's atmosphere. Phosphine is a gas produced by anaerobic bacteria on Earth. It's a potential biosignature. The detection was disputed. Other teams analyzed the data and questioned the findings. The debate is ongoing, but the possibility landed like a bomb. If life is in Venus's clouds, it means life doesn't need solid ground. It could float in the atmospheres of gas giants, living its entire existence in the air, never touching a surface. The sky itself could be an ecosystem. Venus forces us to rethink habitability. We thought Venus was a cautionary tale, a greenhouse effect run wild, a dead world. But if there's life in those clouds, then we've been wrong about what life needs. It doesn't need a surface. It doesn't need mild conditions. It just needs a niche, a pocket of chemistry where metabolism can happen. And Venus might have that pocket, floating 30 miles above hell. These worlds are close. Europa is about 628 million kilometers away. That's far, but it's not interstellar. It's a trip we can make with current technology. Enceladus is about 1.2 billion kilometers. Titan is roughly the same. Mars is as close as 55 million kilometers when our orbits align. Venus is our nearest planetary neighbor, 40 million kilometers at closest approach. We don't need to wait centuries for a probe to reach another star. We don't need to decode radio signals from civilizations thousands of light years away. We might find life in the next decade, with robots, with flybys and landers and sample return missions, with instruments we're building right now. If life started on Earth and Earth isn't special, then life should have started elsewhere in our solar system. Maybe it started on Mars when Mars had rivers. Maybe it started in Europa's ocean and still thrives there today. Maybe it floats in Venus's clouds, drifting through acid mist, completely unlike anything we've ever seen. We're standing in a neighborhood that might be full of biology, different biology, alien biology. Life that proves life isn't rare, just hidden. The question isn't whether life exists beyond Earth. The question is what it looks like when we find it. So, what does alien life actually look like? We're searching our solar system. We're scanning distant planets. But when we find something, will we even recognize it? Or will it be so strange, so completely unlike anything on Earth, that we'll stare right at it and see nothing? Here's the strange part. Life might surprise us, but it might not be unrecognizable, because evolution has a habit, a tendency to solve the same problems the same way, even when there's no connection, no common ancestor, no shared blueprint, just physics and chemistry pointing toward the same solution. We call it convergent evolution. Eyes evolved independently at least 40 times on Earth, 40 separate lineages. Vertebrates developed eyes. So did cephalopods, and arthropods, and box jellyfish, and a dozen other groups that split apart hundreds of millions of years ago. None of them copied each other. None of them inherited the design from a common ancestor with eyes. They all invented it separately. It's like 40 different civilizations inventing the wheel. Once the need exists and the materials are available, the solution is almost inevitable. Light exists. Light carries information. Detecting light gives you an advantage. So evolution keeps building light detectors, again and again. The camera eye structure in humans and octopi is nearly identical. Same lens, same retina, same basic architecture, but we didn't inherit it from each other. Our last common ancestor was a simple, worm-like creature 600 million years ago. It didn't have camera eyes. We built ours from scratch. So did the octopus. An octopus's eye and a human eye are like two smartphones designed by competing companies, built from completely different ancestors, shaped by identical constraints until they look nearly the same. Think about flight. It evolved separately in insects, birds, bats, and pterosaurs. 4 completely different groups, 4 different wing designs, but all of them discovered the same fundamental truth. You need a large surface area. You need it attached to a lightweight frame. You need muscles strong enough to move it fast. The details differ, feathers versus membranes versus chitin, but the solution is recognizable every time. Echolocation evolved in bats. Then it evolved in dolphins. Totally separate lineages. One's a mammal that returned to the sea, the other's a mammal that took to the air. But both hunt in darkness. Both need to navigate without light. So both invented biological sonar. Same problem, same solution. Streamlined bodies show up everywhere. Sharks are fish. Ichthyosaurs were reptiles. Dolphins are mammals. 3 different branches of the tree of life. 3 different body plans to start with. But all of them ended up with the same torpedo shape, because water is water, drag is drag. If you want to move fast through a fluid, physics doesn't give you many options. There's a phenomenon called carcinization. It's the tendency for animals to evolve into crabs. Not metaphorically, literally. It's happened at least 5 separate times. Different species, different ancestors, same end result. Nature keeps making crabs. Hermit crabs aren't true crabs. King crabs aren't true crabs. Porcelain crabs aren't true crabs. But they all look like crabs. They all act like crabs. Because the crab body plan works. Hard shell for protection. Legs tucked underneath for stability. Compact form that's difficult to flip over. Evolution discovers this design over and over. If evolution keeps making crabs here, what forms might it keep making everywhere? Convergent evolution is like different engineers solving the same problem. Eventually, everyone designing a bridge will discover the arch. Not because they copied each other, because physics prefers certain solutions. An arch distributes weight. It resists compression. It stands. Other designs might work, but the arch works best. So you see arches in Roman aqueducts and modern highways and medieval cathedrals. Same shape. Different builders, same underlying physics. Life on another planet faces the same physics we do. the same chemistry. If there's light, detecting it is useful. If there's an atmosphere, moving through it efficiently matters. If there's gravity, structural support becomes essential. These aren't Earth problems, they're physics problems. And physics is the same everywhere. That doesn't mean aliens will look human or even familiar at first glance, but it means they might have features we recognize. If they live on a planet with light, they probably have eyes. Maybe not two eyes, maybe not forward-facing, but some kind of light-sensing organ, because evolution keeps inventing eyes whenever light is available. If they manipulate objects, they probably have appendages, maybe tentacles, maybe jointed limbs, maybe something we don't have a name for yet, but something that grasps, something that holds, because manipulating your environment is useful, and there are only so many ways to grab something. If they move through a fluid, they're probably streamlined. If they need protection, they probably have some kind of shell or armor or thick skin. If they communicate, they probably make vibrations or light patterns or chemical signals. The specific implementation varies. The underlying solution doesn't. We won't find humans on other worlds. We won't find dogs or trees or anything that looks like it belongs in our fossil record. Common ancestry matters. Details matter. But certain features are probable, likely, almost predictable. Aliens might be strange, but convergence suggests they won't be incomprehensibly so. We might look at something and think, those are eyes, that's a limb, that's a mouth, not because we share an ancestor, because we share physics. The universe has rules, chemistry has constraints, evolution explores possibility space, but that space isn't infinite. Some solutions work better than others, and when a solution works, evolution finds it, again and again. On Earth, life keeps rediscovering the same answers, which means life elsewhere might be doing the same thing. We might recognize it when we see it, not because it looks like us, but because it solved the same problems we did. The universe has rules. Evolution finds solutions. Eyes evolve, wings evolve, limbs and mouths and ways to sense the world. That's convergence. That's physics and chemistry guiding life down similar paths. We've seen it happen over and over. The pattern holds. But what about intelligence? Intelligence evolved on Earth. We're here, thinking about aliens, writing scripts, building telescopes. That happened. The question is whether it had to happen, whether intelligence is another convergent solution, like eyes, or whether it's a fluke, a cosmic accident that happened once and might never happen again. Here's where it gets complicated. Intelligence isn't rare on Earth, it's everywhere. Primates figured out tools and social hierarchies. Dolphins and whales have complex communication systems that might qualify as language. Crows and ravens solve multi-step puzzles and remember human faces for years. Elephants mourn their dead and recognize themselves in mirrors. Parrots don't just mimic sounds. They understand concepts, use words in context, make jokes. Octopi escape from locked tanks, unscrew jars from the inside, change color and texture to match their surroundings in milliseconds. Intelligence evolved multiple times, independently, in branches of the tree of life so distant, they barely share biology. Mammals and birds and cephalopods don't think the same way. They don't have the same brain structures. An octopus doesn't even have a centralized brain. 2/3 of its neurons are in its arms. It's a distributed intelligence, a creature that can taste with its skin and solve problems with limbs that think for themselves. Some scientists half-jokingly call octopi the closest thing to an alien on Earth. They're that different, that strange. If we struggle to understand an octopus, how would we recognize something truly alien? Intelligence might not look like problem-solving or tool use. It might look like something we've dismissed as instinct, pattern, or noise. We're biased toward recognizing minds that think like ours. We might have already encountered alien intelligence and not recognized it. Think about what intelligence requires. The human brain uses 20% of the body's energy budget. 20%. Your brain is about 2% of your body weight, but consumes a fifth of everything you eat. Intelligence is like running a Bitcoin mining operation in your skull, burning calories to process information. Every thought has a cost. Every memory takes fuel. The brain is expensive to run. Evolution doesn't keep expensive things around unless they pay off. For humans, the payoff is obvious. We built cities. We invented agriculture and medicine and space travel. Intelligence gave us civilization, and civilization gave us survival advantages that outweighed the cost. The math works. For dolphins, the math is different. They might have language as complex as ours. Studies suggest their communication systems have syntax, grammar, even names for individual dolphins that work like proper nouns. They talk to each other, but they don't have hands. They can't write anything down. They can't build tools or machines or computers to analyze their own language. Intelligence without tools is like having the blueprints for a rocket, but no factory to build it. The ideas are there. The execution isn't. Octopi are intelligent enough to solve puzzles, recognize individual humans, and plan escapes from their tanks. But they're solitary. They don't form societies, and they die before their offspring hatch. Every generation starts from zero. There's no culture, no transmission of knowledge from parent to child. It's like being born with Einstein's brain, but no books, no internet, no teachers. You start from scratch every single time. You might be brilliant, but you'll spend your whole life reinventing the wheel. Intelligence is common. Technology is rare. That's the pattern on Earth. Lots of creatures are smart. Only one built a civilization, which raises the question, is technological civilization an inevitable outcome of intelligence? Or is it a fluke? Did humans get lucky? Did we happen to have the right combination of traits at the right time? Opposable thumbs and big brains and social structures and long childhoods that allow for learning. Take away any one of those, and maybe we're just another smart animal that never builds a radio telescope. Maybe intelligence is convergent. Maybe aliens everywhere evolve big brains and problem-solving skills. But maybe technology isn't. Maybe the step from smart animal to technological species requires a dozen coincidences to line up perfectly. And maybe that almost never happens. Here's the honest answer. We don't know if intelligence is rare or common. We don't even really know what intelligence is. We can't define it for ourselves, and we're supposed to be the smart ones. That should probably concern us when we're planning to look for it in aliens. We recognize intelligence on Earth by behaviors that look familiar. Tool use, communication, problem-solving, self-awareness. But those are human-centric measures. An octopus with a distributed nervous system and skin that functions as a display screen might experience consciousness in a way we can't even imagine. A whale swimming through the ocean, singing songs that travel for hundreds of miles, might be composing poetry we're too deaf to hear. If intelligence can take that many forms on one planet with shared ancestry, what might it look like on a world with completely different evolutionary history? We assume intelligence means curiosity, exploration, the drive to understand and manipulate the environment. But maybe that's just mammal intelligence. Maybe reptile intelligence or insect intelligence or something. We don't have a word, for intelligence looks completely different. Maybe it doesn't build. Maybe it doesn't explore. Maybe it just is, in some way that we wouldn't recognize as thought at all. The problem isn't whether aliens are smart. The problem is whether we'd know it if we saw it. Whether we'd recognize a mind that doesn't think like ours. Whether intelligence written in a different language, running on different hardware, optimized for different problems, would even register to us as intelligence. We might meet them and think we're looking at animals, or plants, or rocks. We carry assumptions about what minds look like. We expect language, culture, technology. We expect beings that want to communicate, that have something to say, that think conversation is valuable. Those are human expectations. They might not apply. This matters for how we search. If intelligent aliens exist, how would we find them? We can't look for big brains or social behavior or tool use. We can't even look for intelligence directly. We have to look for something intelligence produces, something detectable across light years of empty space. We have to look for technology, for signals, for evidence that someone out there is doing more than just surviving, that someone built something that leaks into the cosmos. That's the next question. That's where we turn next. So how do we find them? How do we search for minds that might not think like ours? technology that might not look like ours, civilizations that could be doing things we haven't even imagined yet. The answer is both simple and humbling. We listen. We point our instruments at the sky and we scan for signals, for patterns, for anything that doesn't fit the random noise of the cosmos. This is SETI, the search for extraterrestrial intelligence. It started in 1960 with a project called OSMA, one astronomer, one telescope, 80 hours of listening to 2 nearby stars. They heard nothing, but it was a beginning. The logic behind SETI makes sense once you think about it. We can't visit other star systems. We can't send probes fast enough to matter within human lifetimes. We can't look for alien cities or spaceships directly because they're too small and too far away. What we can do is listen for electromagnetic radiation, radio waves, the same waves that carry our television broadcasts and cell phone calls and Wi-Fi signals. Radio travels at light speed. It passes through dust clouds and empty space without much interference. It requires relatively low energy to produce, at least compared to other ways of sending information across interstellar distances. Any civilization that discovered radio technology would probably use it. Maybe they'd move beyond it eventually, but there'd be a window where radio leaked into space, a period where their planet was shouting into the void, whether they meant to or not. That's what Earth has been doing for about a century. Every radio broadcast, every television signal, every radar ping, all of it radiates outward in an expanding bubble. Right now, that bubble is about 100 light years across. Any star within 50 light years has already been washed over by our earliest transmissions. Reruns of old sitcoms and news broadcasts and radio dramas, traveling through space at the speed of light, getting weaker and weaker as they spread out. By the time those signals reach another star system, they're incredibly faint, weaker than the background radiation of space itself. It's like trying to hear a whisper on the other side of a highway during rush hour. Possible, maybe, if you have sensitive enough equipment, but difficult, very difficult. This raises an obvious question. If we've been broadcasting for a century, has anyone been broadcasting toward us? Are there signals washing over Earth right now, too faint for us to notice, or pointed in the wrong direction, or using frequencies we haven't checked yet? SETI exists to answer that question. Thousands of hours of telescope time, scanning millions of radio frequencies, listening to hundreds of stars, the nearest 1,000 stars, then 10,000, then more. The surveys have grown more ambitious as technology improved. Breakthrough. Listen, which started in 2015, is the most comprehensive effort yet. It's scanning the nearest million stars. It's checking billions of radio frequencies simultaneously. It's using some of the most sensitive telescopes on the planet. So far, nothing. No confirmed alien signals. Plenty of false alarms. Interference from satellites. Glitches in equipment. Natural phenomena that mimicked patterns for a moment before resolving into noise. But no transmission that survived scrutiny. No message that held up under analysis. The universe, as far as we can tell, has been very quiet. In 1974, humanity decided to stop just listening. We sent a message. The Arecibo Observatory in Puerto Rico, at the time the largest radio telescope in the world, transmitted a signal toward a globular cluster called M13. The message was simple, a series of ones and zeros that, when arranged correctly, formed a picture. It showed the numbers 1 through 10, the atomic numbers of key elements, the structure of DNA, a stick figure human, the population of Earth, a diagram of our solar system, the telescope itself. The whole thing lasted less than 3 minutes. 1,679 bits of information, transmitted at the speed of light toward a cluster of stars 25,000 light-years away. The Arecibo message is currently traveling through space. It won't arrive for 25,000 years. That's longer than recorded human history. By the time it gets there, the pyramids will be ancient history twice over. If anyone receives it and sends a reply immediately, that reply will reach Earth 50,000 years from now. We sent a message to a future we'll never see, to recipients who may not exist, to a cluster that will have moved slightly by the time the signal arrives. Here's the thing most people don't know. The Arecibo message wasn't really a serious attempt at communication. It was mostly symbolic, a publicity stunt for the newly upgraded telescope, a way to show what the facility could do. Scientists chose M13 because it was overhead at the right time, and it made for good press, a dense cluster of hundreds of thousands of stars. It sounds impressive, but globular clusters are old. Their stars formed billions of years ago and haven't had much activity since. They're not great candidates for life. The message wasn't about expecting an answer. It was about making a gesture, about saying, even if just to ourselves, that we're here, that we tried. The real work of SETI isn't about sending, it's about listening. And listening is hard. Picture this, the radio spectrum is vast. Frequencies stretch from a few kilohertz up to hundreds of gigahertz. That's billions of individual channels you could broadcast on. SETI can't check them all at once. Even with modern technology, surveys have to focus. They pick frequency ranges that seem most likely. The so-called waterhole between 1400 and 1600 megahertz is popular. That's near the emission frequencies of hydrogen and hydroxyl, the components of water. Some scientists think any civilization would recognize this region as special, a natural meeting point in the radio spectrum. Others think that's human bias, assuming aliens would think like us, would value what we value. Then there's the question of where to point the telescope. There are somewhere between 100 billion and 400 billion stars in our galaxy alone. SETI focuses on the nearest ones, the sun-like ones, the ones with known planets in habitable zones. But that's still thousands of targets, tens of thousands, and each star needs to be observed for long enough to catch a signal if one exists. Seconds aren't enough, minutes might not be, hours maybe. SETI is like standing in the middle of the Pacific Ocean, dipping a single cup into the water and concluding there are no fish because you didn't catch any in that cup. We've barely started searching. The tools are getting better. The Very Large Array in New Mexico can scan large patches of sky simultaneously. The upcoming Square Kilometre Array, which will be built across South Africa and Australia, will be 50 times more sensitive than any existing telescope. It'll be able to detect signals from thousands of light years away, transmissions weaker than anything we can pick up now. If there's a civilization out there broadcasting at the same power level we use for air traffic control radar, ESCA could hear it from dozens of light years away. But even with better tools, the silence continues. Decades of searching, millions of stars examined, billions of frequency channels scanned. No confirmed contact. That absence means something. Maybe we're alone. Maybe civilizations are rare. Maybe they don't use radio. Maybe they do, but only briefly, and we're looking at the wrong time. Windows that open and close across cosmic timescales. Maybe they're out there, but we're looking in the wrong places, wrong frequencies, wrong stars, wrong methods entirely. Or maybe they're listening too. Maybe every civilization goes through the same phase we're in now, shouting into the void, hoping for a reply, scanning the sky with growing sophistication. All of us listening, none of us talking. A galaxy full of civilizations, all waiting for someone else to make the first move, all afraid of the silence, or afraid of what might answer. We've been looking for about 60 years. That sounds like a long time in human terms. In cosmic terms, it's nothing. An eye blink. We've surveyed a tiny fraction of the galaxy, checked a narrow slice of the radio spectrum, used tools that, a generation from now, will seem primitive. The search has barely begun. The silence doesn't prove anything yet. It's just data, or the absence of data. The universe hasn't told us we're alone. It just hasn't told us we're not. So we've been listening for decades, using massive radio telescopes, scanning the sky, hoping to hear something that proves we're not alone. But how many civilizations are we actually looking for? How many should be out there? How do you even begin to answer a question like that? In 1961, a scientist named Frank Drake tried to build a framework, not to give a final answer, but to structure the question. He created what's now called the Drake equation. It's a way to estimate the number of detectable civilizations in our galaxy. Not a prediction, a framework, a way to organize our ignorance. The equation itself is simple. N equals R, Star times, Fp times, Ne times, Fl times, Fi times, Fc times L. Each letter represents a different variable. Each variable is a factor that affects how many civilizations we might find. N is the number we're looking for, the number of civilizations in the Milky Way that we could potentially detect right now. R star is the rate of star formation in our galaxy. How many new stars are born each year? We know this one pretty well. Between 1.5 and 3 stars per year. That's roughly one new star every 4 to 8 months. New suns igniting, new systems forming. That part we can measure. Fp is the fraction of those stars that have planets. We didn't know this when Drake first wrote the equation. Now we do. Nearly all of them. Close to 1.0. Almost every star has planets. The galaxy is full of worlds. Thousands of billions of them. Ne is the number of planets per system that could support life. Planets in the habitable zone. Not too hot, not too cold. Liquid water possible. We estimate somewhere between 0.2 and 0.4 planets per system. About 1 in every 3 to 5 systems has at least one world where life could theoretically arise. That's still billions of candidates in our galaxy alone. Then the equation gets harder. The next variables are unknowns. Guesses built on hopes, built on assumptions. Fl is the fraction of those habitable planets where life actually develops. We have no idea. On Earth, life appeared remarkably quickly, within a few 100 million years of the planet cooling down. Does that mean life is easy? Or did we get cosmically lucky? The sample size is 1. You can't draw a graph from one data point. Fi is the fraction of those life-bearing worlds where intelligence evolves. Again, no idea. Intelligence evolved on Earth, but it took billions of years. And it might be rarer than we think. Bacteria dominated this planet for most of its history. Complex life is newer. Intelligence is brand new. Maybe it's common. Maybe Earth is the only place in the universe where anything has ever wondered if it's alone. Fc is the fraction of intelligent species that develop detectable technology, radio telescopes, television broadcasts, signals we could pick up. Even if intelligence is common, technology might not be. Dolphins are intelligent. They'll never build radio transmitters. How many civilizations might exist that we'd never detect because they don't use the electromagnetic spectrum the way we do? The Drake equation is like a recipe where you know the ingredients exist, but not the measurements. You're trying to bake a cake by guessing whether you need a teaspoon or a gallon of vanilla. The first few ingredients are measured. The rest are pulled from thin air. Put optimistic numbers into the equation, and you get thousands of civilizations in the galaxy, maybe tens of thousands. Put pessimistic numbers in, and you get less than 1. We're alone, the only voices in a silent galaxy. Both answers come from the same equation. It all depends on your guesses for the variables we don't understand. Think of it this way. Estimating the number of alien civilizations is like trying to predict how many people are at a party in a mansion when you're standing in one room. You can hear music, but you don't know if there are 10 people or 1,000. Could be a small gathering, could be packed wall to wall. You just don't know. The equation turns "are we alone" into a multiplication problem, which is comforting until you realize half the numbers are complete guesses. It's structured ignorance, a way of admitting what we don't know while pretending we're being scientific about it. But there's one variable that matters more than all the others. One number that could explain everything we see, or rather, everything we don't see. L, the lifespan of a detectable civilization. This isn't about how long intelligent species exist. It's about how long they remain detectable, how long they broadcast signals into space, how long they survive as technological civilizations. We've been detectable for about 100 years, since we invented radio. Before that, you could have pointed the most sensitive instruments in the universe at Earth and heard nothing but natural noise. The question is how long that window stays open. If the average technological civilization lasts 1 million years, the galaxy should be full of voices. Civilizations overlapping, someone always broadcasting. But if the average lifespan is short, 100 years, 1,000 years, then the galaxy could be teeming with life, but silent. Not because civilizations are rare, but because they don't last. Intelligence might be common. Technology might be common. Self-destruction might be inevitable. We've had nuclear weapons for 78 years. 78 years of holding the power to end ourselves. We've had the ability to detect alien civilizations for about the same length of time. The two capabilities arose together. That might not be a coincidence. Every civilization that becomes detectable might also become capable of destroying itself, and most might not survive the transition. The silence we hear when we scan the sky might not mean we're alone. It might mean that intelligence is common, but survival is rare. We might not be listening for alien civilizations. We might be listening for their ghosts, echoes of societies that existed briefly, burned bright, then went dark, windows that opened and closed before we were around to notice. The Drake equation doesn't answer whether we're alone. It shows us what we'd need to know to answer that question, and it reveals how much we're guessing. The math is clean. The uncertainty is enormous. Plug in one set of numbers and the galaxy is crowded. Plug in another and we're the only ones who ever looked up and wondered. The framework is useful. It tells us what to study, what questions to ask, which variables to try to narrow down. But it doesn't give comfort. It gives structure to the mystery. If the math suggests there should be civilizations out there, why is it so quiet? The Drake equation tells us there should be civilizations out there. The math suggests we're not alone. Intelligence should emerge. Technology should follow. Signals should cross the void between stars. So why is it so quiet? In 1950, physicist Enrico Fermi asked a simple question over lunch with colleagues. They were discussing the probability of extraterrestrial life, the vastness of space, the age of the universe. Fermi stopped mid-conversation and said, "Where is everybody?" That question became the Fermi paradox. The universe is 13.8 billion years old. Earth is 4.5 billion years old. The Milky Way alone contains between 100 billion and 400 billion stars. That's not just a lot. That's more stars in our galaxy than there are grains of sand on every beach on Earth. And most of those stars have planets. Many of those planets sit in habitable zones where water could exist as a liquid. The ingredients for life are everywhere. The universe has had billions of years to work with those ingredients. Even if intelligent life is rare, even if it takes billions of years to emerge, someone should have gotten there first. Here's the problem. A civilization capable of space travel wouldn't need to move fast. Even at 1% the speed of light, slow by cosmic standards, they could send probes or ships to every star system in the galaxy. How long would that take? Between 5 million and 10 million years to colonize the entire Milky Way? That's nothing. The galaxy is over 13 billion years old. Someone should have done it by now. The silence is like walking into a forest that's existed for 1,000 years and finding no trees. We should see evidence everywhere. Megastructures harvesting starlight, self-replicating probes exploring every system, radio signals leaking into space, artifacts, ruins, something. We see nothing. The Fermi paradox is like showing up to a party where the music is playing, the lights are on, the food is laid out, but no one is there. Not even a note explaining where everyone went. In 60 years of searching, we have one anomaly. One, the WOW signal, detected in 1977 by the Big Ear radio telescope. It lasted 72 seconds. The signal was so strong, so clearly artificial in its characteristics, that the astronomer monitoring the data circled it on the printout and wrote, "Wow," in the margin. We pointed telescopes back at that same spot. We listened for years, decades. Nothing. The WOW signal is a voice that called out once in the dark, then never spoke again. It's like hearing someone shout your name in an empty house, and when you search every room, no one is there. That's it. That's the entire list of maybes in 60 years of searching. There are explanations. None of them are comforting. Maybe we're early. Maybe Earth is among the first planets where intelligent life has emerged. The universe is just now reaching an age where complex life can arise. We're at the dawn of a universe about to wake up. We're the first ones to the party, arriving before anyone else. If that's true, We have an enormous responsibility. We're the beginning of something vast. Maybe we're late. Civilizations have risen and fallen long before we existed. We're listening for signals that stopped transmitting millions of years ago. We're searching for empires that collapsed before multicellular life crawled onto our beaches. We missed them. They came and went, and the universe moved on. Maybe they're hiding. This is the dark forest theory, the idea that the universe is full of life, but everyone stays silent because calling attention to yourself is dangerous. What if shouting into the void invites something hostile? What if the civilizations that broadcast their presence get eliminated, and the ones that survive are the ones that stay quiet? What if the silence isn't evidence of absence? What if it's evidence of caution? What if everyone who shouts into the void gets an answer they don't survive? Maybe we're not listening right. We're searching for radio signals because that's what we use. But a civilization 1,000 years ahead of us might communicate in ways we can't detect or recognize. We're looking for smoke signals while they're using fiber optics. We're scanning the wrong frequencies, using the wrong methods, asking the wrong questions. They could be talking all around us, and we wouldn't know. Maybe life is rarer than we think. Maybe the jump from chemistry to biology is so improbable that Earth is a cosmic fluke, one lucky roll of the dice in a galaxy full of sterile rocks. Maybe intelligence is rarer. Life might be common, but intelligence might be an accident, a weird evolutionary path that almost never happens. Earth has hosted life for 3.5 billion years. Intelligence emerged once, just once. In billions of species across billions of years, only one developed technology. Maybe that's normal. Maybe the galaxy is full of bacteria and algae and nothing else. Maybe technology is rarer. Intelligence might emerge, but civilizations might not last long enough to become detectable. They might destroy themselves. Nuclear war, climate collapse, engineered pandemics, artificial intelligence that gets out of control. Every civilization might reach a point where they develop the ability to destroy themselves, and most don't make it through. One explanation for the Fermi paradox is that we're early, that we're at the dawn of a universe about to wake up. There's a darker possibility. We're not early, we're on time. Every civilization reaches a filter, a test, that almost none pass. The silence might not mean life is rare, it might mean survival is. And we're approaching our own filter right now. This is the part that gets me. The silence isn't just puzzling, it's a warning. We've been broadcasting our presence for over a century. Radio signals, television, radar. They've been spreading outward at the speed of light, announcing that we're here. If someone is listening, they know about us, and they haven't responded. Maybe they can't. Maybe they're gone. Maybe they're hiding. Maybe they looked at our signals and decided we're not worth contacting. Or maybe they're on their way, and the message just hasn't arrived yet. Light is fast, but space is vast. A response from a civilization 1,000 light years away would take 1,000 years to reach us. We might be waiting for an answer that won't arrive for generations. The universe is old enough and big enough that we should see someone. We don't. That's the paradox. The math says we shouldn't be alone. The evidence says we are. One of these things is wrong. Either our assumptions about how common life is, or our understanding of what we should be seeing. The silence is data. It's telling us something. We just don't know what yet. We keep listening. Every night, telescopes scan the sky. We search for patterns in the noise, signals that might be artificial, evidence that someone else is out there, wondering the same things we are. The search continues because the question matters, because the silence, however profound, isn't proof. It's just silence, and silence can be broken. The silence is data. It's telling us something. We just don't know what yet. And sometimes, the silence breaks, or seems to. On August 15th, 1977, a radio telescope in Ohio picked up something strange. A signal, strong, focused. Exactly the kind of thing you'd look for if you were searching for extraterrestrial intelligence. The astronomer on duty, Jerry Amon, circled it on the printout and wrote one word in the margin. Wow. The name stuck. The wow signal. 72 seconds of narrowband radio transmission at 1420 MHz. That's the hydrogen line, the frequency that hydrogen atoms naturally emit. It's significant because hydrogen is the most common element in the universe. If you wanted to broadcast a signal that anyone looking would recognize as artificial, you'd choose a frequency every civilization would know. You'd choose hydrogen. The signal was strong, 30 times louder than the background noise. It came from the direction of Sagittarius, deep in the galaxy, and then it stopped. We pointed our telescopes back at that same patch of sky. Nothing. We listened again and again over the decades. Still nothing. The signal never repeated. We don't know what it was. The wow signal is like receiving a single text message from an unknown number that just says hello. When you try to reply or trace it, the number doesn't exist. You're left holding your phone, staring at those 5 letters, wondering if you imagined it, but it's right there in your message history. Real, undeniable, and completely unrepeatable. We've looked for explanations. A comet passing through, releasing hydrogen gas, a satellite reflection, interference from Earth, none of them fit perfectly. The frequency was too narrow, the duration too precise, the direction too specific. Was it aliens? Probably not. The universe is full of natural phenomena we don't understand yet. Radio emissions from magnetars, plasma interactions we haven't modeled, something mundane we just haven't thought of, but we don't really know. That's the honest answer. This is how the search works: detection, excitement, investigation. Usually, a mundane explanation. Usually. Fast forward to October 2017. Astronomers in Hawaii spotted something moving through the solar system. Fast. Really fast. Its trajectory was wrong. Objects orbiting the sun follow predictable paths, curved by gravity. This thing was moving in a straight line. It came from outside, from interstellar space. We named it Oumuamua, Hawaiian for scout or messenger. The first interstellar object we'd ever detected passing through our neighborhood. It was strange, long and narrow, about 400 meters end to end. That's about 4 city blocks laid in a line. It tumbled as it moved, reflecting light in odd patterns. And it was accelerating. Not much, just a tiny bit more than gravity alone could explain. That's unusual. When comets accelerate, it's because they're outgassing. Ice turns to vapor, creates thrust, like a tiny rocket. But Oumuamua showed no signs of a tail. No gas cloud, no debris, just silent acceleration through empty space. Some scientists suggested it could be a light sail, a thin reflective sheet pushed by starlight, the way a sailboat catches wind. The kind of technology an advanced civilization might use for interstellar travel. Was it a probe? An artifact? Evidence of intelligence beyond Earth? Probably not. Exotic outgassing we couldn't detect. Ice with different properties than we're used to. A fragment of a shattered planet with unusual composition. Natural explanations exist. They're just less satisfying than the alternative. Oumuamua tumbling through our solar system was like watching a messenger bottle float past your island. You can see it, describe it, watch it leave, but you never get to open it and read the message. Here's the part that keeps me up sometimes. We almost missed it entirely. Oumuamua was already leaving when we found it, already past the sun, already accelerating outward at 58,000 miles per hour. That's fast enough to cross the United States in 3 minutes. We had one shot to study it as it passed. Barely had time to point our telescopes before it was too far away to see clearly. It's gone now, never to return, headed back out into the space between stars, where it will drift for millions of years before encountering another solar system. If it was a probe or artifact, and we have no evidence it was, we had one chance to examine the only alien object that's ever visited us. One chance. And we couldn't even get close. Space is so vast, and our detection systems so limited, that alien artifacts could be passing through constantly. We'd never notice unless they happened to pass very close, and we happened to be looking in the right direction at the right time. Think about that. The universe could be full of travelers, and we're standing on our island, staring at the horizon, seeing nothing but empty ocean. Then there's Tabby's star, KIC 8462852, a star 1400 light-years away that started doing something strange in 2015. It dimmed. Stars dim sometimes. Planets pass in front of them, blocking a fraction of the light. Maybe 1%, maybe 2%. Tabby's star dimmed by 22%. That's not a planet. That's something massive, irregular, unlike anything we'd seen before. The dimming patterns were chaotic. No regular period, no predictable schedule. Something was blocking the star's light. But whatever it wasn't behaving like a planet or a ring system or anything natural we could think of. Scientists started proposing exotic explanations. A swarm of comets, a shattered planet forming a debris cloud, and yes, some suggested a Dyson swarm, a megastructure built by an advanced civilization to capture a star's energy. Thousands or millions of solar collectors orbiting in formation, the kind of thing a Kardashev Type 2 civilization might construct. Tabby's star, dimming by 22%, is like someone flickering your bedroom light on and off in an irregular pattern. It's strange enough that you check if someone's sending Morse code, even though you know it's probably just faulty wiring. Turns out, it probably is faulty wiring, or rather, dust clouds. Uneven clumps of dust orbiting the star, closer than we initially thought. The dimming patterns match what you'd expect from dust of varying density passing in front of the light. Not as dramatic as a megastructure, not evidence of intelligence, just dust. Natural, mundane, explainable. The universe doesn't care what we find convenient. And then there are fast radio bursts, FRBs, millisecond duration blasts of radio energy so powerful they outshine entire galaxies for 1,000th of a second, then gone. We didn't even know they existed until 2007. Since then, we've detected hundreds. Most come from distant galaxies, billions of light-years away. The distances mean these events happened billions of years ago. We're seeing ancient explosions, frozen in light, just now reaching Earth. The mystery deepened when we found FRB 121102, a repeating burst, same location in the sky, flashing again and again. We traced it to a dwarf galaxy 3 billion light-years away. 3 billion. That's 3 billion years of history between the event and our observation. 3 billion years in which life arose on Earth, evolved, built civilizations, reached for the stars. For a while, we didn't know what caused FRBs. The energy involved was staggering, the duration impossibly brief. Some speculated about neutron star collisions, others about exotic physics we hadn't discovered yet. And yes, a few wondered if they could be artificial. Signals from civilizations so advanced their transmissions look like cosmic disasters to us. Probably not. Scientists argue about this, but most now think FRBs are magnetar flares. Magnetars are neutron stars with magnetic fields trillions of times stronger than Earth's. When those fields snap and reconfigure, they release incredible energy. Fast, bright, brief, exactly what we observe. Every maybe so far has become a probably not. The wow signal, Oumuamua. Tabby's a star, fast radio bursts. Each time we find a natural explanation, or at least, we find an explanation that doesn't require intelligence. Dust and gas and stellar physics and phenomena we're only beginning to understand. That doesn't mean we stop looking. Negative results are still results. Ruling things out narrows the search. Every false alarm teaches us something about the universe. We learn what natural processes can mimic intelligence. We refine our methods, sharpen our tools. When we finally do detect something artificial, we'll recognize it because we'll have eliminated everything else. The pattern holds: initial excitement, investigation, mundane explanation, repeat. It's frustrating sometimes. Every signal that turns out to be a pulsar, every anomaly explained by dust. But the process works. Science doesn't move forward through dramatic revelations. It moves through careful elimination, through patience, through looking at the same data from different angles until the truth emerges. We keep scanning the sky. We keep cataloging anomalies. We keep investigating every signal that doesn't quite fit, because somewhere in that noise, there might be a pattern, a message, evidence that we're not alone. And when we find it, if we find it, it won't look like any of these false alarms. It will be unmistakable, clear, repeatable, real. Until then, we have mysteries, signals we can't quite explain, objects that don't behave as expected, dimming patterns that challenge our models. The universe is stranger than we thought, but strange doesn't mean artificial. It just means we have more to learn. The universe is stranger than we thought. We've been cataloging its oddities for decades. Each mystery adds to our knowledge, and sometimes those mysteries reveal an entirely new category of worlds. For most of human history, we knew of exactly 9 planets, the ones in our solar system. That was it. We suspected others might exist around distant stars, but we had no proof, no way to see them, no way to know if our solar system was typical or some cosmic accident. Then, in 1992, astronomers found the first planets beyond our sun. They orbited a pulsar, a dead star spinning hundreds of times per second. 3 years later, in 1995, we found 51 Pegasi b, a planet orbiting a sun-like star, a world we could compare to our own system. That discovery changed everything. As of 2024, we've confirmed over 5,500 exoplanets, 5,500 worlds circling other stars. The Kepler Space Telescope alone found about 2,700 of them between 2009 and 2018. TESS, the Transiting Exoplanet Survey Satellite, continues the search right now. Every few weeks, we add more planets to the list. The number keeps climbing. Think about the timeline. 30 years ago, we knew of 9 planets. Today, we know of thousands. In a single generation, planets went from maybe rare to basically universal. The data suggests nearly every star has at least one planet. Nearly every star. The galaxy isn't mostly empty space dotted with occasional solar systems. It's packed with worlds, trillions of them, and we've only just started looking. Finding these planets requires clever techniques. You can't just point a telescope and see them. They're too small, too dim, too close to their stars. The light from the star drowns them out completely. Detecting an exoplanet by watching its star wobble is like trying to detect a flea on a dog from a mile away by watching the dog's head shake slightly. You're looking for motion so tiny it barely registers. Yet, we've developed methods sensitive enough to catch it. The radial velocity method measures how a planet's gravity tugs on its star. As the planet orbits, the star wobbles. That wobble shifts the star's light toward red and blue as it moves away and toward us. We can measure those shifts, calculate the wobble, infer the planet's mass and orbit. This method found 51 Pegasi b. It opened the door to exoplanet astronomy. The transit method works differently. It watches for dimming. When a planet passes in front of its star from our perspective, it blocks a tiny fraction of the star's light. The star dims slightly, then brightens again when the planet moves past. It's like detecting a moth flying in front of a spotlight from across a city. You're measuring a change of maybe 1% or less in the star's brightness. The Kepler telescope stared at the same patch of sky for years, watching hundreds of thousands of stars, waiting for that telltale dimming pattern. Direct imaging captures actual light from the planet itself. This only works for large planets far from bright stars, young planets still glowing with heat from their formation. It's incredibly rare. Gravitational microlensing uses a star's gravity as a magnifying glass. When a star passes in front of a more distant star, its gravity bends the background star's light. If the foreground star has a planet, that planet creates a second, smaller spike in brightness. You get one shot. The alignment never repeats, but it works for finding planets we'd never detect any other way. Each method reveals different types of worlds. The diversity is staggering. We've found hot Jupiters, gas giants orbiting closer to their stars than Mercury orbits our sun. Their atmospheres are scorching, sometimes thousands of degrees. We've found super-Earths, planets larger than Earth but smaller than Neptune. rocky worlds with masses 5 or 10 times ours. We don't have anything like them in our solar system. We've found ocean worlds, planets that might be covered entirely in water hundreds of kilometers deep. We've found planets orbiting binary stars, real-life Tatooine sunsets. We've found rogue planets drifting through interstellar space with no star at all. We've found planets where it rains glass sideways, and humans still argue about whether aliens are plausible. The universe is weirder than we thought, and that should tell us something about the life it might contain. Some systems demand attention. TRAPPIST-1 sits 40 light-years away. That's close in cosmic terms. About 235 trillion miles. If you could somehow drive there at highway speed, the trip would take about 400 million years. But 40 light-years means the light we see from that star left during the Cold War. We're looking at the recent past. The system contains 7 Earth-sized planets, all roughly our planet's diameter and mass. 3 of those planets orbit in the habitable zone, the region where liquid water could exist on the surface. 7 Earth-sized worlds around one dim star, and 3 of them might have oceans. We've gone from knowing about a few potentially habitable places in our solar system to finding systems like TRAPPIST-1, whole families of worlds that could support life. The question isn't whether places exist where life could survive. We know they do. The question is how we possibly check them all. Earlier sections covered what life needs: water, energy, organic chemistry, time. We know the ingredients now. We've studied extremophiles thriving in conditions we once thought impossible. We've explored the moons of Jupiter and Saturn, found subsurface oceans, hydrothermal vents, chemistry that mirrors the origins of life on Earth. That expanded our view from Earth to our solar system. A dozen or so candidates for life, all within reach of our spacecraft. Exoplanets expand the search by orders of magnitude, thousands of worlds. Most we'll never visit. Most we'll never even image directly, but we don't need to go there. We can analyze their atmospheres from here. When a planet transits its star, some of the star's light passes through the planet's atmosphere before reaching us. Different molecules absorb different wavelengths of light. Oxygen absorbs certain colors. Methane absorbs others. Water vapor leaves its own signature. By splitting the starlight into its component colors, we can identify which molecules are present in that distant atmosphere. Analyzing an exoplanet's atmosphere is like smelling someone's breath from across a room and deducing what they had for lunch. You're looking at the faintest chemical traces in starlight filtered through an atmosphere billions of miles away. The James Webb Space Telescope can do this. It's designed to study exoplanet atmospheres in detail, to look for biosignatures, combinations of gases that might indicate life, oxygen and methane together in an atmosphere, water vapor, carbon dioxide, phosphine. The presence of certain chemicals doesn't prove life exists, but it narrows the field, tells us where to look harder. We're not just finding planets anymore, we're interrogating them, asking, what's in your air? Is there water? Are there chemicals that shouldn't coexist unless something is producing them? This is the exoplanet revolution. Not just the discovery that planets exist around other stars, the realization that we can study those planets, probe their atmospheres, search for signs of life without ever leaving our solar system. We've built tools sensitive enough to detect a moth in front of a spotlight from miles away, instruments that can smell the chemical composition of air on a world trillions of miles distant, technology that lets us survey thousands of planets in a few decades. The scope has changed. We're no longer limited to the few moons and planets we can reach with probes. We're searching a galaxy full of worlds, each one a possibility, each atmosphere a mystery. Each detection method adds more planets to the catalogue, more targets for atmospheric analysis, more places to check for the chemistry of life. The search has become vast, but the tools have become precise. And somewhere among those thousands of confirmed exoplanets, among the tens of thousands we'll discover in coming decades, there might be a world with an atmosphere that doesn't make sense, oxygen where it shouldn't be, methane paired with oxygen, chemistry that demands an explanation, a signature that points to life. But the search isn't only outward. It's not just telescopes scanning distant star systems and probes analyzing exoplanet atmospheres. Some of the strangest encounters might be happening right here, in our own skies, witnessed by trained observers, tracked by military sensors, documented in official reports. These are the events we can't explain. In November of 2004, the USS Nimitz Carrier Strike Group was conducting training exercises off the coast of Southern California. For several days, the ship's advanced radar systems had been detecting objects behaving in ways that made no sense. They would appear at altitudes above 80,000 feet, higher than any known aircraft operates. Then, they would drop to just above sea level in less than a second. An object moving from 80,000 feet to the ocean surface in under a second is like watching a passenger jet dive from cruising altitude to ground level faster than you can blink, then stop without crashing, without decelerating gradually, without any visible means of propulsion. On November 14th, 2 FA-18 Super Hornets were directed to investigate. Commander David Fravor and Lieutenant Commander Jim Slate were the pilots. What they encountered was an object shaped like a white tic-tac, no wings, no visible exhaust, no rotors or propellers, hovering just above the ocean surface. When Fravor descended toward it, the object mirrored his movements. Then it accelerated, vanished from sight in under 2 seconds. No aircraft on Earth can do that. A few moments later, the object reappeared on radar 60 miles away. It had traveled 60 miles in less time than it takes to read this sentence. The Nimitz encounter involved objects tracked on radar, infrared, and visual confirmation. 3 different sensor systems. 3 different types of detection, all recording the same phenomenon. It's like 3 different witnesses with 3 different cameras all filming the same ghost. You can dismiss one sensor as malfunctioning. You can't dismiss multiple independent systems detecting the same object, performing the same impossible maneuvers. The pilots weren't the only witnesses. Radar operators aboard the Princeton, a guided missile cruiser, tracked the objects for days. Infrared gun cameras on the FA-18s recorded them. Multiple trained observers, multiple sensor types, all documenting something that shouldn't exist according to our understanding of physics. What made the movements impossible? The acceleration. Objects were recorded accelerating at rates exceeding 600 times the force of gravity, 600 Gs. An object accelerating at 600 Gs would turn a human pilot into soup. The G-forces would liquefy your organs. Your bones would shatter. Your blood would pool and separate. Witnessing something move like that is like watching a car accelerate to 5,000 miles per hour in 2 seconds without a rocket engine or any visible means of propulsion. Just instantaneous acceleration. No build-up, no exhaust plume, nothing. The objects also showed no signs of creating sonic booms despite moving at hypersonic speeds. When anything travels faster than sound, it creates a shockwave. A boom you can hear for miles. These objects moved at speeds that should have shattered windows and rattled the ships below. Silence. Some reports described transmedium travel, objects moving seamlessly from air into water without slowing down. Water is 800 times denser than air. Aircraft can't just plunge into the ocean at high speed and continue moving. The impact would tear them apart. These objects reportedly transitioned between mediums as if density didn't matter. For decades, this is where the story would end. Pilots would file reports. The reports would disappear into classified files. Careers would be damaged. Witnesses would be discouraged from speaking. The topic was taboo, professional suicide for anyone in uniform. Something changed. In 2017, the Pentagon released gun camera footage from the Nimitz encounter and 2 other incidents. 3 videos. Flyer 1. Gimbal. Go fast. Grainy infrared recordings showing objects moving in ways that military pilots couldn't explain. The footage was authenticated. These were real Department of Defense files. Not hoaxes. Not internet fabrications. Official releases. In 2020, the Pentagon established the Unidentified Anomalous Phenomena Task Force, a formal office dedicated to investigating these encounters. The name changed from UFO to UAP, Unidentified Anomalous Phenomena. attempting to remove the stigma, encouraging military personnel to report sightings without fear of ridicule. In 2023, Congress held public hearings. Military witnesses testified under oath. David Grosh, a former intelligence officer, claimed the government possessed retrieved craft of non-human origin. Ryan Graves, a former Navy pilot, described encountering unexplained objects regularly during training missions off the East Coast, objects that would hold position in hurricane-force winds. David Fravor recounted the Nimitz encounter in detail. The Pentagon's official position is that these objects are real, not sensor errors, not weather balloons, not classified US aircraft undergoing testing. They exist, they were detected, and we don't know what they are. That's the official government stance. Not we investigated and found nothing, but we investigated and we're baffled. Think about what that means. The most advanced military on the planet. Sensors capable of tracking objects thousands of miles away. Radar systems that can distinguish a bird from an aircraft. Infrared cameras that can detect heat signatures through clouds. All of this technology confirming the presence of objects performing maneuvers that violate known physics. And the official conclusion is we don't know. For decades, reporting a UFO would end a military pilot's career. Now, Congress is holding hearings. Task forces are being established. Witnesses are testifying publicly. Something shifted. Either the phenomena became more frequent, or the willingness to acknowledge it changed. Either way, the conversation is no longer confined to fringe researchers and conspiracy theorists. It's happening in congressional hearing rooms. The question isn't whether these objects exist. Multiple credible witnesses and sensor systems confirm they do. The question is what they are. Drones from a foreign adversary? Possible, but the technology would represent a breakthrough that leaps past anything publicly known. Atmospheric phenomena we don't understand? Possible, but why would natural phenomena only appear near military installations and carrier strike groups? Sensor artifacts or glitches? Difficult to explain when multiple independent systems detect the same objects simultaneously, or something else. Technology that isn't ours. Craft designed by an intelligence we haven't identified. We don't really know. That's the honest answer. The data suggests objects that exhibit no visible propulsion, that accelerate at rates that would destroy any known material, that move at hypersonic speeds without creating sonic booms, that transition between air and water without resistance. If these observations are accurate, then either we're witnessing technology that breaks known physics, or our understanding of physics is incomplete. Both possibilities are unsettling. The Pentagon investigated 144 UAP reports between 2004 and 2021. Of those, they could explain only one. 143 remain unidentified. That doesn't mean 143 alien spacecraft. It means 143 cases where the available data doesn't lead to a definitive conclusion. Some might be advanced drones. Some might be sensor malfunctions we don't understand yet. Some might be atmospheric phenomena that mimic the appearance of craft. But what if even one report is something else? What if even a single encounter represents technology from a non-human intelligence? The implications would dwarf every other scientific question we've explored. We've spent this entire journey discussing how we might detect life across interstellar distances, how we might recognize biosignatures in exoplanet atmospheres, how we might interpret radio signals from civilizations thousands of light years away. But if even one UAP represents visitation, then the conversation changes completely. We're not searching anymore. We've been found. The challenge is distinguishing between we don't know what this is and therefore aliens. The gap between those two statements is enormous. Unexplained doesn't mean extraterrestrial. It means unexplained. The absence of an answer isn't evidence for a specific answer. Mystery isn't proof. Yet we're left with credible witnesses, multiple sensor confirmations, objects performing maneuvers that challenge our understanding, and an official acknowledgement that something is happening that we can't explain. That combination is worth examining. Not with certainty, not with claims, but with curiosity, with rigor, with the willingness to say, we don't know and mean it. The Nimitz encounter happened nearly 20 years ago. The footage was released 6 years ago. Congressional hearings happened months ago. We still don't have definitive answers. The objects remain unidentified. The phenomena remain anomalous. We have more questions than answers, which raises another question. If contact happened, if we confirmed without doubt that we're not alone, what would we actually do? We've spent most of this documentary looking outward, searching, wondering. But what happens when the search ends? What do we actually do if we find something looking back? There are protocols for this, official plans, documents with signatories and guidelines and carefully worded procedures. They exist because someone, decades ago, realized we should probably think this through before it happens. First contact protocols are like having a fire extinguisher in your kitchen. You hope you never use it, but if the moment comes, you're glad someone thought ahead, even if the instructions are more guidelines than hard rules. The SETI post-detection protocol is the primary framework. It was established in 1989 by the International Academy of Astronautics. The steps are straightforward on paper. If you detect a signal that might be extraterrestrial, you verify it first. You check for errors. You rule out human interference. You make absolutely certain it's not a satellite, a radar bounce, or someone's microwave oven. Then, once you're confident, you notify other observatories. You share the data. You get confirmation from independent sources before you tell anyone else. Only after verification do you inform international authorities. The International Astronomical Union, the United Nations Office for Outer Space Affairs, your own government. Then, and only then, do you make a public announcement. That's the theory. The protocol also says we shouldn't reply without international consultation. No single person, no single institution, no single nation decides alone what humanity says back. We're supposed to discuss it, debate it, reach some kind of consensus about whether we respond at all, and if we do, what we say. The United Nations Office for Outer Space Affairs would coordinate. They'd bring together governments, scientists, ethicists, representatives from across the globe. Everyone gets a voice. Except, there's no enforcement mechanism, no penalty for breaking the rules. The protocol is voluntary. It's a gentleman's agreement among scientists who recognize the stakes. But if someone detects a signal and decides to announce it immediately or reply without asking permission, there's nothing stopping them. No law, no binding treaty, just a strongly worded document, and the hope that cooler heads prevail. There's another wrinkle. If we detect a signal, it's almost certainly old. Radio waves travel at the speed of light, which sounds fast until you remember how far apart stars are. A signal from the nearest star system would take over 4 years to reach us. A signal from a civilization 1,000 light years away would have left their world before the Norman conquest, before the printing press, before anyone on Earth knew the Americas existed. We'd be listening to a message sent by beings who might not even exist anymore. Their civilization could have risen, flourished, and collapsed while their signal crossed the void. Any reply we send would take just as long to arrive. Sending a message to aliens and waiting for a reply is like shouting into a canyon and waiting for an echo. Except the echo might take 100 years to return, and when it does, the voice that answers might not be friendly. That's where game theory enters the picture. Contact between civilizations can follow different paths. Mutual cooperation is the optimistic scenario. Both sides gain. We share knowledge, culture, technology. They help us, we help them. Everyone benefits. It's possible. It's the scenario most SETI scientists hope for. But it's not the only option. There's mutual assured destruction. Both sides have the capability to harm each other, so neither acts. A kind of cosmic standoff, a cold war across light years. Tense, but stable. Then there's asymmetry. One side is far more advanced than the other. One side has all the leverage. One side decides what happens next. And history suggests that scenario rarely ends well for the less advanced party. We have examples, centuries of them. First contact between human civilizations has a pattern. The more technologically advanced culture usually dominates, sometimes through conquest, sometimes through disease, sometimes through economic exploitation. The outcomes vary, but the dynamic is consistent. When two civilizations meet, and one has a significant advantage, that advantage gets used. Not always maliciously, not always intentionally, but it happens. The Aztecs met the Spanish. The Aboriginal Australians met British colonizers. The Native American tribes met European settlers. In every case, the less advanced civilizations suffered. Cultures were destroyed. Populations decimated. Languages lost. The intentions of the arrivals didn't always matter. The power imbalance did. There's no reason to think contact with an alien civilization would be different. If they can reach us and we can't reach them, the imbalance is already there. They choose when contact happens. They choose the terms. We react. That's not a position of strength. This line of thinking leads to a darker possibility, the dark forest theory. It was popularized by Chinese science fiction author Liu Cixin, but the idea has been around in various forms for decades. The universe is like a vast forest at night. Every civilization is a hunter with a gun. You stay silent because any noise might reveal your position to something bigger and hungrier. If you announce yourself, you risk drawing attention. And attention, in a universe where resources are finite and intentions are unknown, is dangerous. The safest strategy is to stay hidden, to listen but never speak, to observe but never reveal yourself. If every civilization follows this logic, the universe stays silent, not because it's empty, because everyone's hiding. The Fermi paradox isn't a mystery. It's evidence that intelligence breeds caution, that survival means silence, that the civilizations we can't detect are the ones that learned this lesson. The ones that didn't are already gone. It's a grim thought, but it's grounded in logic. If you don't know who else is out there, if you don't know their intentions or capabilities, broadcasting your location is a gamble. You're betting that whoever hears you is friendly, or at least indifferent. You're hoping they're not expansionist, not resource-hungry, not threatened by your existence. That's a lot of hope to stake on a signal sent into the void. Here's the unsettling part. We've already made that gamble, without asking permission, without a global debate, without any real consensus about whether it was a good idea. In 1974, the Arecibo Observatory in Puerto Rico sent a message into space, 3 minutes long, aimed at a globular star cluster called M13, about 25,000 light-years away. The message contained information about humanity, our biology, our DNA, our location in the solar system, the basics of mathematics and chemistry. It was a postcard, a friendly hello, a bottle tossed into the cosmic ocean. One scientist, one telescope, one decision. Frank Drake and his team designed the message. They sent it. There was no international consultation, no UN resolution, no vote, no lengthy debate about whether humanity should announce itself to the universe. They just did it. And that message is still traveling, still carrying our address into the void. It won't reach M13 for 25,000 years, but it's out there, permanent, irrevocable, active. SETI continues. Messaging extraterrestrial intelligence, sometimes called METI, sends signals deliberately, not just listening, but broadcasting. Teams have transmitted messages toward nearby star systems, high-powered radio pulses, mathematical proofs, cultural information. Each message is another flare shot into the dark forest. Stephen Hawking warned against it. He argued that any civilization capable of receiving our messages would be far more advanced than us, potentially by millions of years. And advanced doesn't mean benevolent. It means capable. If they decided we were a threat, or a resource, or simply in the way, we wouldn't have a say in what happened next. He urged caution. He suggested that maybe, just maybe, we should keep quiet until we understood the risks better. We ignored him. The broadcasts continue, not frequently, not with massive resources behind them, but they happen, and each one is a decision made by a handful of people on behalf of the entire species. The choice about whether to contact aliens was made decades ago. The message is already out there, traveling at the speed of light, growing fainter as it spreads, but never stopping, never fading completely. It's too late to take it back, too late to reconsider. We announced ourselves, and now we wait. We wait to see if anything answers. We wait to see if the forest is empty or if something in the dark heard us. The protocols we've written, the consultations we've planned, the careful procedures we've established, they all assume we get to choose when contact happens. They assume we're the ones searching. They assume we'll have time to prepare, to discuss, to decide as a species what we want to say and how we want to say it. But if something already received our message, if something is already on its way, those protocols don't matter. The decision was made for us, by people who believed the risk was worth taking, who believed that silence was lonelier than the danger, who believed that reaching out was fundamentally human, even if the consequences were uncertain. We'll find out if they were right. Whether it takes decades, centuries, or millennia, we'll find out. The message is traveling, and we can't call it back. We've sent our message, traveling outward, growing fainter but never stopping. What happens if something actually hears it? What would contact really look like? Not the way we imagine it. We picture spaceships descending, diplomatic envoys stepping onto the White House lawn, aliens asking to speak to our leader. That assumes they think like us, that they have ships, that they care about nations, that they want to talk at all. They might communicate by altering the orbit of stars. They might have already made contact, and we interpreted it as a pulsar. We're waiting for a knock on the door, when they might have already sent a letter we used as kindling because we didn't recognize the language. The reality would be stranger than invasion or peaceful greeting. The reality would be asymmetry. Any civilization we detect is almost certainly far older than ours, far more advanced. The math makes this inevitable. Humanity has been using radio for about 100 years. That's the window where we're detectable. Before radio, we were silent. After radio, we might move to something else. Lasers, quantum communication, technologies we haven't imagined yet. 100 years is nothing on cosmic timescales. If we detect another civilization, we're catching them in their 100-year window. Or their technology is so widespread, so permanent, that it's still visible long after they stopped using it. Either way, they're ahead of us. Think about how far ahead. The Kardashev scale measures civilizations by energy use. Type 1 harnesses all the energy of their planet. Every earthquake, every lightning strike, every photon hitting their surface. Type 2 harnesses the energy of their star. They might build a Dyson sphere, a shell that captures all the light from their sun. Type 3 harnesses the energy of their galaxy, billions of stars, all feeding their civilization. Humanity is currently type 0.73. We're not even on the scale yet. We use fossil fuels, solar panels, wind turbines. We're children playing with matches compared to what's possible. A type 2 civilization could disassemble planets for raw materials, not as an act of war, as routine construction, the way we mine iron or harvest timber. They might take apart Mercury to build solar collectors. They might reshape their entire solar system, and we would see it from light years away. We'd see the star dim as they built around it. We'd call it a mystery, give it a name, study it for decades, never realizing we're looking at someone's engineering project. The gap between us and a million-year-old civilization would be like the gap between an ant colony and the International Space Station. The ants wouldn't recognize the station as technology. They'd walk across a circuit board and think it was terrain. They'd crawl through a computer and never understand they were inside something designed, something built. We might be doing the same thing right now, walking through their machines, living inside their experiments, calling it nature because we don't know what else to call it. Compare modern humans to humans 10,000 years ago. 10,000 years ago, we were just beginning agriculture, just starting to build permanent settlements. Now we have spacecraft, quantum computers, genetic engineering. That's 10,000 years of progress. A million-year head start would be that leap multiplied by 100. We can't comprehend it. Our brains aren't built to imagine that distance. If a Type 2 civilization wanted Earth's resources, negotiating with us would be like you negotiating with the bacteria in your gut before taking antibiotics. The conversation wouldn't happen. Not because they're cruel, Because the power imbalance is so extreme that dialogue becomes meaningless. You don't consult bacteria. You don't explain your decisions to them. They exist on a different scale of relevance. That's hard to accept. We imagine ourselves as partners in conversation, equals meeting equals, sharing knowledge, trading culture. That's the optimistic version, the one where they're only a few thousand years ahead, close enough that we're still recognizable as peers. But if they're a million years ahead, a billion, we might be to them what bacteria are to us, beneath notice, or interesting only as a curiosity, something to study, not something to talk to. There's another asymmetry, time. A civilization that lives around a red dwarf star could develop for trillions of years. Red dwarfs burn slowly. They'll outlast our sun by a factor of hundreds. A civilization with that much time might experience time differently. They might think in centuries, the way we think in seconds. A human lifetime would pass for them, like a single breath passes for us. They might look at humanity the way we look at mayflies. Interesting because we live fast. Irrelevant because we're gone so quickly. What would contact mean under those conditions? Would they even recognize us as intelligent? We build cities that last hundreds of years. They might build structures that last millions. By the time they noticed our signal and decided to respond, we could be extinct. Our entire civilization could rise and fall in the time it takes them to compose a reply. Here's the part that keeps me up at night. If we detect a signal, we'll be listening to the past. Radio waves travel at light speed. That's fast by human standards. But space is vast. A signal from a star 100 light years away was sent 100 years ago. By the time we hear it, that civilization might be long dead, or so advanced they've moved beyond radio entirely, abandoned it the way we abandoned smoke signals. We wouldn't be making first contact. We'd be discovering their fossil, their last words, echoes from something that no longer exists. The universe might be full of these echoes, transmissions from civilizations that died centuries or millennia ago, still traveling outward, still carrying their message. But the sender is gone. We could spend centuries calling back to ghosts, transmitting replies to coordinates where nothing listens anymore, waiting for responses that will never come because the civilization died thousands of years before we heard them. The search for extraterrestrial intelligence might actually be a search for extraterrestrial obituaries, a catalogue of the dead, species that reached out, announced themselves, then vanished before anyone could answer. That would still mean something. It would mean intelligence arises, that we're not alone in that sense. But it would also mean intelligence doesn't last, that the window between developing technology and disappearing is narrow. So narrow that two civilizations almost never overlap. We'd be surrounded by evidence of life, proof that others existed. But we'd never meet them, never speak to them. We'd be alone in a graveyard, reading tombstones written in radio waves. Or maybe some of them survived. Maybe some of those signals come from civilizations still alive, still transmitting, waiting centuries for a response, patient in ways we can't fathom. They sent their message knowing their great-great-great-grandchildren might be the ones who hear the reply. If they think in terms of grandchildren at all, if they reproduce, if they die, we don't know. We're guessing based on the only example we have, us. Contact wouldn't be an event. It would be an archaeological discovery, a historical find. We'd decode their transmission, learn what we could, send a reply into the darkness, then wait. Wait to see if anything is still there. Wait to see if they remember sending the original message. Wait to see if they care. That's what contact would mean. Not ships landing, not diplomatic exchange. Asymmetry, distance, bimeu. Messages in bottles thrown across an ocean, so vast that the bottles arrive centuries after the sender drowned. We'd learn we're not alone, but we'd also learn that alone is the default state. That meeting someone, truly meeting them, might be impossible. The universe too big, the timing too narrow, the gap between us and them too vast to cross. We'd still try. That's what makes us human. We'd still send the reply, still wait for the answer, still hope that somewhere, someone is listening, even knowing they might be gone, even knowing we might never hear back. We'd reach out anyway, because the alternative is silence. and we've already decided we can't live with that. Here's what we've really been asking this whole time: not whether aliens exist, but whether we deserve to meet them. The search for extraterrestrial intelligence is humanity holding up a mirror and asking, if we met ourselves out there, would we survive the encounter? Think about what that mirror shows. Humanity has existed for roughly 300,000 years. That's longer than our species has had language, art, agriculture. 300,000 years of looking up at the stars. But technological civilization? 200 years. Just 2 centuries since we started building machines that could change the world. Nuclear weapons have existed for 78 years. A single human lifetime. In that time, we've built enough to destroy ourselves several times over. Climate change, artificial intelligence, synthetic biology. Every existential risk we face, we made ourselves. We search the stars for intelligence while simultaneously questioning whether our own intelligence will destroy us. It's like building a telescope with one hand and a bomb with the other, hoping we figure out which one to use first. The question isn't just, will we find aliens? It's, will we survive long enough to look? Every radio telescope pointed at the sky is a statement of hope, a belief that there's something worth finding, that we'll be here long enough to find it. That intelligence is not a temporary condition that self-terminates before it reaches the stars. That's what the search really means. Not finding them, proving that survival is possible. The real surprise isn't whether aliens exist, it's whether civilizations survive long enough to meet each other. If the universe is full of intelligent life that destroys itself within a few centuries of developing technology, the galaxy could be teeming with graveyards, worlds where intelligence arose, built cities, invented telescopes, looked up at the stars with wonder and hope, then went silent. We might be searching for company in a cemetery, calling out into a darkness full of bones. Or we might find someone who survived their own adolescence, someone who made it through the filter we're struggling with right now, someone who can show us it's possible. That's the hope encoded in every signal we send, every frequency we monitor. Every dollar spent on the search is a bet that we'll be here to receive an answer. That intelligence doesn't have to be a brief flicker, that it can endure. We are both the seekers and the thing we fear finding. Violent, exploitative, short-sighted. Our history is written in blood and fire. We've destroyed entire ecosystems, driven thousands of species to extinction, built weapons we hoped we'd never use, used them anyway. If we encountered another species like us, would we trust them? Would we survive them? Would they survive us? That's the question we're avoiding every time we look up. We talk about whether aliens are friendly or hostile, whether they'd come in peace or conquest, whether we should hide or signal. But the question isn't about them, it's about us. Are we the threat we fear finding in the stars? The act of searching is an act of hope, a declaration that we believe intelligence can survive its own power, that curiosity can outlast violence, that wonder can overcome fear. Every time we point a telescope at the sky, we're saying we believe in a future, that there's something out there worth meeting, that will become something worth meeting too. Remember that bubble of radio signals we talked about at the beginning? The sphere of broadcasts expanding through space at the speed of light, carrying our voices into the void. That bubble is a test, not of whether anyone is listening, of whether we're worth answering. If someone out there receives our signals, what will they hear? A species that destroyed its own world, or one that learned to save it? A civilization that turned its technology toward war, or one that chose survival? The answer depends on what we do next, not them, us. The search for aliens forces us to confront what we value, what we fear, who we want to be. It asks whether we're worthy of the universe we live in, whether intelligence like ours deserves to continue. We don't know the answer yet. We're still writing it. Every radio telescope is a monument to that uncertainty, a statement that we're still here, still looking, still hoping, that intelligence is more than a cosmic mistake, that consciousness doesn't have to end in silence, that somewhere out there, or sometime in the future, minds can meet across the darkness and recognize something familiar, not aliens, Just another species that survived, another world that made it through. That's what we're really searching for. Not proof that we're not alone, proof that making it is possible, that the great filter isn't inevitable, that intelligence can grow up. The universe is waiting to see if we will. If you've made it this far, thank you for taking this journey. If you enjoyed it, consider subscribing. There's more to explore, more questions to sit with, more reasons to look up. For now, just picture this: a telescope pointed at the sky, somewhere on Earth, right now, listening, waiting, hoping. It's an act of defiance against the darkness, an act of humility before the infinite, an act of faith that we'll be here tomorrow to keep searching. That telescope is us, still reaching, still wondering, still believing there's something worth finding, still believing we're worth finding too.